Great. Well, thank you all for joining the first USPA webinar. And this is the USPA Technical Training Webinar Series. And my name is Ming Xiao. I'm a professor of civil engineering at Penn State. And I'm also the president-elect of the US Permafrost Association, or USPA. Today, we're going to have the first USPA webinar, Permafrost Overview, with Professor Vladimir Romanovsky. Dr. Vladimir Romanovsky is a Professor Emeritus of Geophysics at the University of Alaska Fairbanks, UAF. He was the past president of USPA and a past vice president of the International Permafrost Association. He led the Geophysical Institute Permafrost Laboratory at UAF. His work involves internationally coordinated research on permafrost temperature changes in Alaska, Russia, Canada, Greenland, and Mongolia. He conducts numerical modeling of past, present, and future permafrost dynamics and remote sensing of permafrost and periglacial processes. The webinar series is sponsored by GeoWatersheds Scientific, Shannon and Wilson, P&D Engineers, Arctic Foundations, or AFI, BD Streams, and individual sponsor, Catherine Schneider. So with that, I'm going to turn your attention to Dr. Romanovsky. And so this is a webinar format. And although you won't be able to speak or show your video, but you can type in the questions under the Q&A session. And we'll have maybe several minutes in the end to answer your questions. And you can type questions anytime you want, and then in the end, and I'll be the moderator and read out the questions. Okay, so with that, Dr. Romanovsky, so you can get started, please.
Yeah, thank you very much, Ming, for the introduction, and also thank you for all who participating in this webinar, for your interest in permafrost. I was asked to present some kind of general knowledge about permafrost, so it will be most of the presentation will be pretty basic, and of course in 50 minutes I cannot cover this topic in depth, because it's really a very huge topic and very exciting right now. So we'll start with definitions, and then we'll go a little bit into properties and maybe just some ideas about how permafrost could be protected from thawing. That's actually not exactly my area of expertise. That's probably the farther or later webinars, which will be involved. Presentation from engineers will be actually more kind of informative for you. But we'll start with common definitions of permafrost, just to speak the same language. So first of all, definition of permafrost. It's in the past, permafrost came from this permanently frozen ground, but very soon scientists recognized that it's not really permanent, and then just not to change the name, we just decided not to call it permanently frozen ground, but perennially frozen ground. So it means that many years ground is frozen, and if so, that we'll call it permafrost. So a formal definition based on permafrost temperature is permafrost is rock, sediment, ice, any other earth material with a temperature that remains at or below 0 degrees Celsius for 2 or more consecutive years. So this is a temperature-based definition. There are several other definitions of permafrost, and we will discuss a little bit limitations of this definition. So it's first of all, I want to say that when we say earth material, we don't think about sea ice. We don't think about perennial snow or glacier ice, though some permafrost scientists, few of them, believe that glacier ice should be included in permafrost, but I don't think we shouldn't do it because the glaciologic community is much larger still than permafrost community, and they will, beat us up if we will we will try to do that. So, from my point of view, glacier ice is a separate topic, though it may fit the definition. But the ground ice is part of the permafrost, and we actually will, in this presentation, I will try to show that it's very important part, and maybe one of the most important part of permafrost is ice. But because the definition doesn't include any words about ice, it's just temperature. So that's why we have to add some clarification or specifications to when we say it is permafrost, depending how much ice is in the permafrost. That's why there are several kind of this sort of specifications or clarifications. When permafrost includes some ice, we call it ice-bearing permafrost. So it's below zero, but and also there is some ice present. If this ice not just present, but hold the particles of the material or soil material together, then we call it ice-bonded permafrost. So that's kind of the most common understanding what permafrost is in everybody's mind. So when really ice is in the frozen ground, and this ice is holding the soil particles together. But in some cases, it could be like dry frozen permafrost, where temperature is below zero, and by this temperature definition, it is permafrost, but there is no water. Well, in this case, actually, an example could be or very dry, say, sand or bedrock with no fractures. In this case, of course, most of the physical properties not changing when the 0 degrees Celsius threshold is crossed. So there is no really difference in properties of this material. If it's below 0 Celsius or above 0 Celsius, almost no difference. And finally, there is some interesting material, which is called cryopeg. It's a soil saturated with concentrated solids, which enough salinity to keep these solids not frozen at the given temperature. So it's also by definition is below zero, and by definition it is part of permafrost. However, it's not frozen in our sense. There is no ice, and material properties mostly the same as unfrozen material properties. So that's keep in mind when you think about that just 0 degrees Celsius based definition of permafrost. So in some cases, we have to add this specification to be clear what we are talking about. But most of the time, I would say we are talking about ice-bonded permafrost. That's the most common kind of situation in the frozen environment in the Arctic and subarctic. So now, permafrost could be has some different special distribution. And first, look at this northern hemisphere permafrost distribution map. So everything colored is permafrost areas, and in a kind of dark gray area is non-permafrost areas. So, and this is just the northern hemisphere. So you can see that permafrost is product of cold climate, and the concentration of permafrost is in the high latitudes or high elevation. So high latitudinal permafrost and mountain permafrost or elevation permafrost or alpine permafrost, like Tibet Plateau and other mountains in Central Asia, also Alps. And also the different colors represent different continuity in terms of spatial distribution of permafrost. So the kind of bluish color is continuous permafrost. It means that you can find permafrost pretty much everywhere in this area, except maybe for big rivers or very big and deep lakes, there may be no permafrost. Otherwise, it will be pretty much everywhere. And discontinuous, all other colors, it's discontinuous permafrost. And it means that you can find permafrost and non-permafrost at the same general area, geographical area, but under different surface conditions. In some locations there will be permafrost, and in some locations there will be no permafrost. And it doesn't mean that permafrost is disappearing or something like this. It's just different conditions, surface conditions, will give you a situation where you can preserve permafrost in one conditions, but you don't have permafrost in other conditions. And it could be pretty stable if climate and anything else will not be changing, then that situation will persist forever. So that's, and there is some subsea permafrost. There is some shells, very shallow, well, relatively shallow depth water, and there is some permafrost. It's much more difficult to map subsea permafrost. There's lots of efforts now to make a little bit more, create a little bit more knowledge about it, but we will not be talking about subsea permafrost in this presentation because it could be a separate, big presentation, and somebody else can present on that topic. So that's pretty much general distribution and general properties. So to kind of distinguish, and it's kind of important, there is important difference. There is some layer above permafrost, and it is not part of permafrost. We call it seasonally frozen ground. Or it could be seasonally frozen ground where no permafrost at all. So that's the layer which is one part of the year is in frozen state, and the same layer will be not frozen in other part. Of course, in the winter it will be frozen, in the summer it will be not frozen. And that layer is on top of permafrost, and it could be from few decimeters to several meters in thickness, and we shouldn't include it in permafrost for sure because it doesn't fit the definition. So it's not, we need 2 years of material frozen to call it permafrost. So the layer above permafrost usually, and here some kind of different people call it differently, but usually the seasonally thawed layer above permafrost called active layer. It's kind of typical situation. And then the layer which freezing during the winter, but there is no permafrost. Usually people call it seasonally frozen layer. However, I think to keep this definition very strict, I think the best way to say seasonally thawed layer if it's above permafrost and it's refreezing completely during the following winter, and seasonally frozen layer where it's frozen only during the winter and there is no permafrost below it. So that's towards definitions. Now, just warning, there is some, you can find even in published literature, something like this, active layer of permafrost. So it's wrong. So now you know, active layer is not part of permafrost. You cannot say that. Or another one, very upper layer of permafrost that thaws every summer and refreezes every winter. It is active layer. Again, wrong, because permafrost cannot be not frozen during the summer. It's not permafrost. 2 years, remember, at least 2 years, you need to know. You can, and then you can call it permafrost. And frozen permafrost, thawed permafrost, there's kind of a little bit awkward. And sometimes you can understand what people means when they say, for example, thawed permafrost, it's a layer which was permafrost in the past, and then it's thawed. So how you call it? Well, you'll find some different name for that a little bit later. All right, so just be aware that this when you say something like this, people who involved in permafrost research will be not exactly trustful, towards you and say, if he knows anything about permafrost. Anyway, so now, like I said, ground ice is very important component of permafrost, and we will spend some time talk about ground ice. Again, very general, just to show what the form of it, maybe a little bit how it get into the ground. So first of all, we can distinguish some distributed ice and massive ice. And for, say, engineering purposes, it's also very important because massive ice usually, that's where you have the most amount of ice content in permafrost when you have massive ice. But sometimes distributed ice could be also, could occupy pretty good portion of the soil, of the frozen soil. So let's think about distributed ice first. Okay, again, there is special science, part of the permafrost science talking about this form of ice in the permafrost. It's very generally, we can distinguish between ice cement and ice lenses. So ice cement usually crystals of ice between the particles of soil, so small you cannot see it even. But in lenses, ice lenses, you can see it, just with naked eye. I will just give you some photos just to illustrate. So here we have upper part of this core is ice cement. So you cannot really see ice crystals, but they are there. It's frozen ground. But in our lower part, you already see some kind of lenses of ice. And the same thing here. So this is pretty much all ice cement. So no visual ice, but it is there. And actually, you will be surprised that about, and this, it is silt, frozen silt, and about 40% of this material is actually ice still, and you may not see it very well. Well, in this case, you see very, very nicely these ice lenses here in the core. And in this case, the volume of percentage of volume occupied by ice could be up to 60, 70%, and only 30% will be the material, the mineral soil. So another example. So, okay, so, but generally, this distributed ice generally has, when permafrost is just has distributed ice, it's the percentage of volume occupied by ice usually lower than when you have the massive ice. And the massive ice also can get into the permafrost in different ways. And again, it's true, I would spend too much time to describe all of the how it get there, but I will try to just give you some very general ideas. So in massive ice, we can think about segregated ice lenses, where you have big lenses like it was on the previous slide, but much thicker and much more extent laterally. And that we'll call segregated ice or buried ice. It's also common in an area which was presently not glaciated, but it was glaciated in the past. The ice, glacier ice, could be buried under material, and then it turned into frozen state. And in this case, we include this buried ice into the permafrost layer. So that's one thing. And then the most common, especially in Alaska, the most common form of massive ice is ice wedges. And there is some intrusion ice. And I will give you just a few photographs illustrating how it looked like. So this is, well, this is Yamal Peninsula, and there is still lots of debates if it's this layer, this white layer is ice. And there is debates, if it's segregated ice or it's buried glacier ice. Well, we will not get into this discussion, but just for scale, how large the ice layer is, the people for scale. So you can imagine the cliff here is about 30 meters high. So about at least 20 meters layer is ice. And in Yamal Peninsula, it's a very typical feature, and it covers large areas where you have about 10 meters of frozen material and then about 20 or 30 meters of just pure ice under it. So that's our segregated or buried ice in the Yamal Peninsula. and there are some other areas where this ice is present. Now, like I said, the most common ice is ice wedges, and they also could be very different. In this case, it's kind of very, I would say, extreme case of amount of ice. All this white material is ice, and it's ice wedges, huge ice wedges, and dark material in between. It's a frozen material, also has ice in it as well. So altogether, percentage of this ice in this kind of permafrost could be up to 90, even 95% of volume. And I will just give you again several photos showing another person for the scale and looking at this ice wedges. So we are talking about, again, about 30 meters of cliff with lots of ice in it and some frozen material in it. This is previous slides were from Siberia. This is from Alaska. It's actually Ben Jones here for scale of the ice wedge here. This is Kalama River on the right. There's lots of, again, ice wedges in it. When ice wedges are melting, they're showing how much of material, how much of the volume was occupied by ice, leaving this kind of pyramid type of ground, which is slowly thawing and kind of collapsing. So it's called bite rocks, but don't bother to remember that. And sometimes the material is ice is so much, see in this case, that the frozen material is still there in between of ice wedges, and all ice already melted, and all this open space was actually occupied by ice not so long time ago. Okay. This is, I think, it's good example of ice wedges because you can see on the cliff, the ice wedges on the cliff. This is the same area. This is just cliff showing how it looks like here. But you can also look on the top. So these ice wedges actually create these polygons. They could be, sexagons. It could be just 4 sides, and it doesn't, in different material, it will be a little bit different shape. But the main thing is they create this network of ice wedges. If you look from the top, and they go under each of this small trough is ice wedge, an ice wedge going into the ground. And depending on the how this ice wedge was formed, it could be several meters in across and several meters in depth, or sometimes it up to like 5-6 meters across and many meters, like 10 meters, 20 meters, 30 meters in depth. And this is one of this very icy permafrost in Italic River in North Slope of Alaska. So this is from the paper by Misha Kanevsky and co-authors. Again, people for the scale, and that's about 30 meters cliff, which most of the material here is ice. And from this paper, we can learn how much of ice in this material. So this is ice wedge. So this is how much of the total volume occupied by this pure ice, ice wedges, so massive ice. And you see that at some depth, and this is depth from 0 to 32 meters, so it's 32 meters cliff. At some places, ice, the pure ice occupies up to 80%. And together with ice in the rest of the frozen ground, we can have more than 90% of volume ice in this kind of permafrost. And I can imagine if it's 30 meters cliff and it's 90% ice, if this material will thaw and ice will melt, out of 30 meters cliff will only 3 meters left of this muck, oversaturated material. So you can imagine what could happen to anything which is based on the top of this very ice-rich permafrost. And here in Alaska, the area with this type of ice showed in dark gray. So it's not uncommon. It's not uncommon, and unfortunately, around Fairbanks we have this kind of ice. We have a belt on the northern foothills and southern part of the North Slope of Alaska. We have on the northern of the Seward Peninsula. So anyway, so all this area you can find this type of ice in the ground, and it's still there. So just very short, how this ice got into it. So the thing is that because of so-called climate, and during the freezing, active layer is freezing very quickly, and materials start to get very cold. And because it's getting cold, it shrinks, and some small crock appear. It could be just a few centimeters wide and 5-6 meters deep. But in the spring, when snow will melt and this empty crock, water will go into it and freeze because it is permafrost. The temperature is below zero all the time. So it will create a small ice vein, but because this repeating every year, and for several 1,000 years, you can develop a pretty thick or wide ice wedge. So that's how it works. I will not go into details because we just don't have time, but if somebody interested, we can talk about it later. So another type of ice is intrusive ice, which creates features very well known as pingo, and this is one of them, and the Prudhoe Bay area. So it's old picture. There's still some funny turtles here, but now they remove them because it's not kind of it's not correct to put something on natural environments. But there's some other couple more photos of the pingos here, and another one very interesting one. It was older one, and then it started to collapse, and then created new one. So there's very interesting features, and usually they have pretty thick kernel or core of ice, pure ice in it. So that's another form of massive ice, and it's usually happen during the refreezing of drain lakes. And this is kind of schematic diagram showing how it happens. Again, I don't have time to discuss it too much, but again, if somebody interested, we can talk about it or later today if there will be questions, or maybe we can make another seminar and we can talk in details and the parts of I'm talking. So again, coming back, what's the most general and important permafrost characteristics? Well, spatial distribution, we talk about it. We will talk about temperature separately because it's really important, even definition based on temperature. The thickness of permafrost, so how thick it is. Well, in the thickest permafrost in the world is in East Siberia, and it was about 1,400 meters. And this is the known thickness. So maybe some places it's even deeper. In Alaska, the thickest permafrost is in the Prudhoe Bay area, and it's about 650 meters. And we will talk a little bit about it on the next couple slides. So thickness of the active layer, again, it's not part of permafrost. It's important characteristic still, in the permafrost areas. Depth to you can think about it as a depth to the permafrost table, so to the top of permafrost. And of course, ice content and unfrozen water content, it's also important. But again, we will not get into details here. So, and we're fortunate to have this pretty detailed permafrost map for Alaska, which was created by a group of scientists. Thor Jorgensen was leading this group, and it was established by the last conference, which was held International Permafrost Council, which held in Fairbanks, 2008. So this shows continuity of permafrost in Alaska, continuous, discontinuous, and some sporadic and isolated masses. But also this map shows the thickness of permafrost, which I was just talking about. So typically in the continuous permafrost, zone, we have depth of permafrost or thickness of permafrost several hundred meters, generally speaking. In a discontinuous permafrost, generally speaking, we have about less than 100 meters of thickness of permafrost. But there is some interesting places in discontinuous zone, like in the Bethel area, where temperature of permafrost is minus 0.2. So it's really, really warm permafrost. But at some boreholes, permafrost was measured, the thickness of permafrost 180 meters, or 100 meters. So generally, of course, discontinuous warm permafrost is thinner than continuous and colder, but there is some exceptions as well. And that's very interesting why it's so. By the way, it's open question still. So the same map has also some additional few maps which show much more interesting material, permafrost temperatures, ground ice distribution. Of course, it's kind of very general distribution, saying if a lot of ice there, or it's not that much. So the ice content is the very difficult parameter to really get information on. And very often in permafrost engineering, this is the less known parameter of permafrost, but it's, in most cases, it's the most important parameter. Okay, now, excuse me. Now we're going into permafrost temperature. And this is kind of schematic and most common representation of distribution of permafrost temperature with depth. So this is depth, this is temperatures here, and this is example of actually pretty warm permafrost. So the permafrost here is about minus 1 degree Celsius. So it's kind of, and the thickness of permafrost is just 25 meters. It's very, it's thin and warm permafrost. You can find such permafrost around Fairbanks or in other locations in interior Alaska, for example. And here you see that there are several things which is important. So the temperature, if you measure temperature continuously, you can draw the minimum temperature with depth, and that will be this part of the trumpet curve, so-called trumpet curve. And then you can draw also the maximum temperature during the year. And we will create this so-called, engineers call it trumpet curves, which shows where temperature in the soil, in the material, could be during these seasonal variations. But because the permafrost is good low passing filter, these variations will disappear. And for warm permafrost, the depth of this penetration of these seasonal variations will be somewhere between 7, sometimes even less, to 15 meters maybe. In cold permafrost, this depth will be deeper. It will be like more like 15 to 25 meters. But below this depth, there is no seasonal variations, and temperature is more or less changes much more slower, I would say. But it's changes, and I will show you what's going on with this temperature now. And on this presentation, see, it's the straight line. So now, the crossing the maximum temperature in 0 degrees Celsius will give you the top of permafrost. See, it's by definition, below this point in depth, all temperatures are negative during the whole entire year. So that's definition of permafrost. But upper part, it's thawing during the summer, but then refreezing completely during the winter. So that's your active layer or seasonally thawed layer. All right. We measure temperature in boreholes to establish this kind of temperature profiles, and we're using different technique. I don't have time to talk about it. And as a snapshot, we can establish, like, for example, this case, it was during the IPY, it was lots of efforts to establish the snapshot of permafrost temperature distribution in a whole entire permafrost regions, not only in the Northern Hemisphere and not only in North America, but North America is shown here as an example. And colors represent the temperatures in permafrost. And usually when you say permafrost temperature, In the past, people would refer to this depth of 0 degree Celsius variations. I'm sorry, depth of 0 seasonal variations. So seasonal variations 0, and that's temperature usually called permafrost temperature. But not all depth, not all measurements are such deep. So sometimes you can use shallow depth and you calculate mean annual temperature, but you have to refer at what depth your temperature you're referring. It should be just to understand where we are. But again, from the different distribution of temperatures, it's pretty straightforward. So colder permafrost in the north and south and interior, it's a discontinuous permafrost. You already have all colors here, including red, which is not permafrost. It is normal. Now, but what is interesting that in the cold permafrost, by the work of Lackenbrook and colleagues, it was established that remember we say that below the 0 annual amplitude variations of temperature, it is straight line down to the bottom of permafrost. Well, it was recognized that that is not straight line, and maybe it was straight line sometimes in the past, but now most of the temperature profiles, they have this curvature, and Art Lackenbrook and colleagues, they interpret it as a warming. Recent warming in climate make near surface permafrost warmer, and instead of this straight line, we have these curvatures. And when you get into the data what we are collecting, so this is 20 meters, this is 55 meters, and all these 55 meters, the gradient is opposite. So the temperature in permafrost getting colder with depth, not warmer like it should be because of geothermal heat flux. No, it's getting colder and substantially colder. So now at the depth horse side, our near surface permafrost 20-meter depth is about -5.5 or even warmer, but at 55 meters it's still -7. So it's like almost 2 degrees colder at depth instead of getting warmer and warmer with depth. So that's definite indication of recent warming. And sure enough, our data showed that this warming happening pretty much all across Alaska, much more warming happening in the colder permafrost, much less in warm permafrost, but it's happening everywhere. And mostly in this slide, I show the air temperature, mean annual air temperature, and mean annual ground temperature at the surface at the top of permafrost and 20-meter depth. And this increase in temperature in the ground in permafrost following very closely on a long-term basis the trend of warming in air temperature. And it's happening not only in Alaska, it's happening all over the world, except maybe a little bit less in some parts of Antarctica. But pretty much in the northern hemisphere, we have almost all of them. So this is the trends, and we have just few blue points here in the trend, which is show cooling during this time period, which is actually it was actually last maybe 20, 30 meters records, and during this period of time, only few points are showing some decrease in temperature. Pretty much all rest of them show some of them very significant increase, some of them maybe less. Now, all this warming, how it's goes into permafrost degradation. So, of course, when permafrost is getting warmer, it's already some sort of degradation of properties, and engineers know about it. But the major thing is when permafrost starts to thaw. And for that, there is some kind of global database, CALM database, which shows that permafrost is thawing already in many areas from the top down. What it means that this active layer thickness is increasing this time. But it's increasing, obviously, in some locations like West Siberia or European North, but much less. This trend is you can see this trend in Canada or North Slope of Alaska. However, there is some evidence that active flare increasing and the depth of thawing is increasing as well. Now, just looking at this high resolution satellite photos showing these ice wedges we are talking about start to melt from the top. And it's melting, create these big troughs, usually filled with water, or not necessarily. And this is the definite and very strong indication that summer thaw is increasing. There's another example in a very, very cold permafrost. It's Isaacson Island in Canadian archipelago. Permafrost temperature is -15 here. But if you compare photos, our site from 2005 and 2016, so in 2005 it was very flat, no indication of any subsidence. Here, in 10 years later, all the surface is very, very uneven, and there's lots of subsidence going on. Well, because of penetration of summer thaw is getting deeper and deeper, and upper part of ice wedges start to melt. And because it's pure ice, the surface kind of following the top of the ice wedge, following, developing these troughs, what we're talking about. So this is how permafrost thaw in cold climates. In what it shows that the permafrost temperature could be very low, and permafrost thermally could be stable, but you still can have thawing of permafrost going on just because of summer conditions. And that create big problems for, well, not only for ecosystems like this abrupt thaw example, but for infrastructure as well. So even in cold permafrost, where traditionally building the cold, natural cold is used by building any kind of infrastructure on one of the engineering way to kind of keep permafrost in cold state, to elevate the building above the surface using these piles. So elevating the buildings, what we do, first of all, we not allow heat from the building going to the ground, but also we allow during the winter time, and there is no snow under the building, actually make ground much colder. And actually it works very good in engineering. So however, even in cold permafrost, and even we keep this permafrost cold, the summer penetration of thaw may affect, in the cold permafrost, may affect this infrastructure by melting of ice, which I showed you in natural conditions. The same process even in higher rate happening when you have infrastructure on the permafrost for some reasons, and collecting of snow and some other things, disturbance of the surface. And in this case, the building, even in cold permafrost, could be in trouble already by just increase in the active layer thickness. And this is good example from Point Lay village, where this picture we're taking, where original surface was somewhere like here, and now we see that lots of subsidence and piles already not holding very well. So what's really happening here? In the past, when climate was cold enough, the summer penetration of thaw was not deep enough to get to the ice wedges, and winter cooling kept this situation intact. However, with increase in temperatures and summer penetration of the thaw, it happened that actually the part of these ice wedges started to melt. Again, permafrost temperature is still -6 in Point Lay, but the process is going on simply because of summer thaw is much deeper and winter freezing is less. And now we have this problem. We have this problem with infrastructure, and we call it hanging stairways village, because when it was built just maybe 30 years ago, 35 years ago, this building, the level of the ground was here, and now it's at least 1.5 meters, sometimes 2 meters, and sometimes even more below the original surface of the ground. So one of the, and I am not addressing any engineering questions here, but just from this discussion, as an example, one way of protect a permafrost from further thawing and degradation, in this case, when temperature is still low and we still natural cold here, what we need to do, we need just to make something to protect this ice from further melting. And the kind of natural way to do it, just put some barrier with some material, pretty much any kind of material, which will make this distance between surfaces here and surface of ice wedges here. Now, if you fill these troughs with some material, say silt, now distance from here to here, and your summer penetration, even if it's deeper now than it was, say, 20, 30 years ago, it will not reach ice here anyway. And winter cooling will be enough to keep the system frozen, and you can actually restore the situation intact. So it means that in cold permafrost, you have to think about not only keep permafrost cold, which is still cold, but also to make this penetration of summer thaw minimum. And then you will be in good shape in terms of engineering. Now, and of course, it's very general statements I'm making, because there is some cases where even in cold permafrost, at some locations, in some conditions, permafrost could be getting warm and even get very close to 0 degrees Celsius, even in cold permafrost regions. Now, in the warm permafrost, it's much more difficult, because with all this warming, bringing permafrost in the temperatures very, very close to 0 degrees Celsius, and permafrost is not only warming, but also thawing. So this is example from Fairbanks area, Bonanza Creek area, where permafrost is already thawing from the top down. What happening here, so in the cold permafrost, we were here, where seasonal thaw ground will freeze completely during the summer, during the winter time, and permafrost will be more or less stable. So now we're crossing, in warmer permafrost, we're crossing this kind of threshold where the thawing is deeper than freezing during the winter time. And we create a layer, we call it talik. Well, unfrozen permafrost, right? That's not right. Talik, where it was permafrost. But now, because of these conditions, the summer thaw is deeper than seasonal freezing, and we're creating this layer of material which is not freezing at all during the winter, talik, and it creates much more problems for engineering structures. It's not only in Fairbanks area, it's all in interior Alaska. Right now, we are at this threshold. At some locations, few locations, we're already crossing it. At some locations, we are very close to cross it. And of course, it will creating of these taliks will further melt ice and create subsidence and big subsidence like in this pictures, and infrastructure will be impacted because of that. And in this case, engineering solutions is much more, I would say, expensive. So in this case, you really have to do something to make permafrost stable and not create this talik. One of the solutions is this thermopiles, but this is definitely not my topic. You probably will be talking about it in your next webinar. So thank you very much on that. And any kind of questions, I'm ready to answer now, or if there will be some desire, we can have another meeting and web presentation in the future, where you can ask me to go into more details in some part of what we discussed today, or some other questions about permafrost. So thank you very much.
Thank you, Professor Romanovsky, for this challenging overview, because it's so much content to discuss, and you're able to give us kind of a summary. There are some questions, and I'm going to read out to you, and perhaps you can also see that under the Q&A tab. So the first question is, what is the key distinction between ice-bearing and ice-bounded permafrost?
Mm-hmm. Ice-bearing is just it's notification there is some ice, but it's not necessarily holding the pieces of the soil together. So, and ice bounded, it's where ice is really hold the material together. So it's mostly difference in mechanical properties of the material. So when it's ice bounded, it's behave as a pretty hard material. If it's ice bearing, not bonded but just bearing, so that's much softer material. And the cause of it could be salinity, for example. So there is some salinity, there is some on the big pores, there's ice. In the smaller and more concentration solids, there is no ice, and a material is a whole in the mass has much weaker mechanical properties than ice bonded permafrost.
Thank you. Is there any distinction between active layer and seasonally frozen ground, or are those two terms used synonymously?
Well, like I said, active layer is actually jargon, scientific jargon. Better, from my opinion, better to have very strict, definition saying seasonally thawed ground or seasonally frozen ground. So that's much, there's no ambiguity. Active layer, some people understand as a just seasonally thawed ground. So it's the case when it's above permafrost. It's during the summer it's thawed, and during the winter it's completely frozen. And some people call it only that situation active layer, but some people extend it to seasonally frozen layer as well, where you don't have permafrost, you have only seasonally frozen layer, and some people call it active layer, and it's make it ambiguous. So that's why if you really want to say very clearly, just say it seasonally thawed layer for layer above permafrost, and seasonally frozen layer when it's not permafrost.
Thank you. Can you give some general information about the spatial distribution of epigenetic and syngenetic permafrost?
Well, that's a big question, really. The general thing is the syngenetic permafrost. Well, I didn't even define syngenetic permafrost. So I will go to actually map, which well, I think, yeah, this permafrost map of Alaska, that will be a good example here. Yeah. So if you look, if you have this map, and actually it's available, so you can get it. Epigenetic permafrost is when surface is not changing too much during this formation of ice. Even if it's like many thousands of years, surface more or less the same. Maybe it's actually, there is some sedimentations going on, but it could be just like half a meter or so. In this case, you're developing epigenetic ice wedges, and they like in this map of ice wedges in Alaska, they will be late Pleistocene. Holocene. Holocene red, Holocene ice wedges. So Holocene ice wedges in red, that will be almost for sure. It will be epigenetic ice wedges. There's also Holocene ice wedges on the north slope of Alaska, which are formed during the last 10,000 years. So that will be also pretty much all epigenetic ice wedges. But all these yellow dots, that will be your late Pleistocene large syngenetic ice wedges, because during the formation of these ice wedges, it was very high rate of accumulation of the silt material from surrounding periglacial areas, both on the north and the south. And accumulation rate was like meter for 1,000 years, and even much more than that in some places. And you develop ice wedge not only of, kind of horizontally, just cracking in the same position, but also vertically, because this cracking and developing ice wedge into the sides also grow it up and up and up. So, but this is like, it's very, difficult to explain it in a very short kind of answer. It is very interesting phenomena, and it's very important because the syngenetic ice wedges has much more ice in it, and for infrastructure, that's definitely will be nice to know how deep the ice is going into the ground. And by the way, in Point Lake, I mentioned that those big syngenetic ice wedges going below the sea level. So it means that if they melt all, the ground may be below sea level. So that's the size of the problem.
What about the age of a permafrost?
Age of permafrost could be very different from just very, very young and just some few years of the existence to more than a million years in age. So very, very kind of long range, big range of ages. Typically, the youngest permafrost you will find in a warmer environment, where permafrost just building. So the youngest permafrost and shallower permafrost building in warmer environments, kind of close to the southern boundary of permafrost distribution, and all permafrost you may find in the cold, thick, and continuous permafrost in the north.
Well, because
and you can distinguish like very recent permafrost, like Little Ice Age permafrost exists, Holocene permafrost exists, late Pleistocene permafrost exists, and actually in some places it's older than Pleistocene.
Thank you. I'm going to ask the one last question from the audience. This is probably a big question. Can you talk about your recent publication suggesting the near-surface permafrost will be gone by the end of this century? And then can you describe a near-surface?
Yeah, this is, well, I will try to answer quickly. So near-surface permafrost, the term, which was, well, I think maybe even it's myself who introduced it in late 90s, but why we have to introduce this term? Well, in the past, when permafrost was stable, say all permafrost science was developing during the 60s and maybe 50s, 60s, and 70s, where it was not such a thing as a global warming. There was actually global cooling even with the worry about global cooling in the 60s and early 70s. And that time, it was not necessarily to distinguish, this near-surface permafrost, because permafrost was more or less in equilibrium, in this climate. And where permafrost was, it was from the, pretty much the top of permafrost and down to the bottom. And where is no permafrost, there was no permafrost at all. So the recent warming, especially during the last 40, 30 years warming, permafrost started to thaw from the top down. And now there is some situation where there is no permafrost in the upper, say, 5 meters, but there is still permafrost from 5 to 500 meters. So in this case, you have to say something about this upper part, which are much more dynamics. And that's how this near-surface permafrost was introduced. Because when you map permafrost, you say there is no permafrost, but to what depth? So if you have situation like in Seward Peninsula, for example, or some other places where permafrost top is already below the surface and maybe at some 5-meter depth. But below is still permafrost. Is it permafrost area or not? Should you include it or not? So then you have to say it is permafrost there, and that's permafrost area. But there is near surface permafrost is absent. There is no very strict definition of how deep this near surface permafrost. Typically, we're talking about maybe 5 meters, 10 meters, probably something like this. Shallower than 10 meters, that's near surface permafrost. And necessity of this term became, it became necessary to introduce this term because of the recent dynamics of permafrost, because of recent climate warming. And about this paper, well, that's the model which used was very simplified model, mostly following the changes in climate. And that paper actually mostly about climate, but the comparison of the situation in terms of climate now and 3 million years ago, which was another warm period. And arguments was that during that time, permafrost was not existing in most places where it exists now, but with projections of climate, with kind of most aggressive warming, like RCP 8.5, for example, where the warming by the end of the century will be in, say, North Slope of Alaska will be 7-8 degrees Celsius. With this kind of warming, we are getting into the same climate which was that during that optimum 3 million years ago. And by analogy, permafrost will be disappearing. But again, the only near surface permafrost will be disappearing, but deeper permafrost will still be there for actually centuries and maybe millennia. To thaw 500 meters of permafrost, it really will need lots of time, long time. That's why we have to introduce this term near surface permafrost.
Thank you, Professor Romanovsky. Just a heads up, and right after this seminar, I'm going to send out a post-webinar survey, and you can type in any questions. And if we have enough interest on some specific questions, we can ask Professor Romanovsky to come back and give us a more in-depth webinar. And so this concludes our today's webinar. And I also have your questions, some of them are not answered. I'm going to ask Professor Romanovsky. So thank you all for joining us, and thank you, Professor Romanovsky.
Thank you. Thank you for your attention and interest. Bye-bye.
Okay, bye-bye.